Hello students, welcome to EPG Pathshala. I am Dr. Sanjay Kumar Chamoli from the Department of Physics and Astrophysics, University of Delhi. Today we are going to talk on module Radiation Detectors Part 5 under the paper Nuclear and Particle Physics. After completing this module, the students will be able to grasp the knowledge of various modes of detector working. They will be able to understand the basics of pulse height analysis of radiation detectors. Also, they will get an idea about the energy resolution of detectors. Radiation detectors mode of working. The detectors can be operated in the following two modes. Number one, the current mode. So modes of working means what is the way out for getting the output voltage, getting the output of the detector. Because we know that the detectors give only the charge. Whatever radiation enters in the detector, it interacts with the material of the detector and produce charge carriers. The charge carriers can be either the electron ion pairs, as in case of charged particles, or it can be basically the electron hole pairs. So basically the charges are getting produced in the detector material, within the detector. These charges are getting collected. Now, in order to get the desired output, we have two choices that how our output can be obtained from those charges. So in that way we can see that our detectors have two choices in which they can be operated, which we are calling as two modes. Number one is the current mode. In this mode, an average DC current is measured over a period of time. That is, electrical signals from individual interactions are averaged together, forming a net current signal. Example in case of GM counter. So this is very important thing that in the case of GM tube, they basically give us an average electrical signal, which is the result of individual interactions. So GM tubes, we know that GM tube is basically a gas detector. So this GM tube basically operate in the current mode. Another important property in the working of detectors in the current mode is, in this mode, all information about the individual interactions is lost. Also, net current in the current mode, net current is proportional to the dose rate in the detector material. And this mode is applied in detectors used at very high interaction rates. Another important way of taking out the detector, the charge collected in the detector is via pulse mode. So we can say that our detector is working in the pulse mode. In the pulse mode, what happens is, in this mode, signal from each interaction is processed individually. So net information on the amplitude and timing of the signal is obtained. So we can say that in case of current mode, the information about the individual pulse is lost. So in that case, in the case of current mode, what we have learned is that we get the average of all the pulses, all the individual pulses, and a net pulse is resulted in the output. So we basically cannot get information about the individual interactions. But here in case of pulse mode, each interaction is processed individually. So it means whatever radiation interactions are happening in the detector, each interaction is giving you the pulse, and that pulse is basically recording individually. So here we can basically identify the type and the energy of the incoming radiations. So net information on the amplitude and timing of the signal is obtained in the pulse mode. This is the big advantage of asking our detector to work in this mode. Example, gamma ray detectors for spectroscopy. So when the gamma ray detectors are used for spectroscopy, that is to understand the energy systematics in the particular reaction, then we can use the gamma detectors in the pulse mode. Properties of pulse mode. What are the basic properties when the detectors operate in the pulse mode? The important properties are: number one, amplitude of each pulse is proportional to the energy deposited in detector by the interaction causing that pulse. So as I told you that interactions are happening in the medium of the detector, and each interaction is generating an individual pulse. So depending upon what is the type of the radiation and how much its energy, we get a definite pulse of the detector. And since each pulse is processed individually, so we can identify what radiations have interacted with the material and of what energy. So properties of pulse mode, the first important property is amplitude of each pulse is proportional to the energy deposited in the detector by the interaction causing that pulse. In this mode, the second important property is, in this mode, the initial signal comes from a charge pulse and is then converted into a voltage pulse by a charge sensitive preamplifier. So this is another important property, that when we put our detector to work in the pulse mode, we need to connect a charge sensitive preamplifier which converts the current, which converts the voltage pulse, which converts the charge collected into a voltage pulse. Radiation detectors mode of working. So we continue our discussion about the properties of pulse mode of working of detectors. Here in this slide, the detector is given and its electrical equivalent is shown. So a detector is electrically equivalent to a capacitor and a resistor connected in parallel. A resistor is nothing but a load resistance and across which we measure the voltage. If time constant tau is equal to RC is large, then during the charge collection time in the detector, the capacitor is charged. It means when the radiation interact, charges are created. That is, if they are charged particles, then electron hole pairs are produced. If they are photons, then electron hole pairs are produced. These electron hole pairs or electron ion pairs need to get collected at the electrode. So during the charge collection time in the detector, the capacitor is charged. Once charge collection stops, the capacitor discharges through R. So when the capacitor discharges through R, we can find what is the time constant, because time constant tau is given as equivalent to or equal to RC. Time to maximum voltage is determined by the charge collection time in the detector material. So until and unless the entire charge passes through R, we cannot get the maximum, we cannot achieve the maximum voltage. So the output voltage becomes maximum when the charge collection time in the detector with the charge collection time in the detector material, which sets the lower limit. Radiation detectors modes of working. So we continue our discussion about the properties of pulse mode of working of detectors. We are going to study the timing characteristics of pulse mode of working. Now here in this case, the amplitude of output voltage, because in the previous slide we have seen that the output voltage is measured across the load resistance. So here we can say that our output, what we get out of the detector, is basically the output of the preamplifier. So amplitude of output voltage is proportional to the charge generated in the detector, that is energy deposited by the radiation in detector. So here on the right hand side, one picture is shown where the behavior of detector current is shown as a function of time. On the lower panel, production of voltage or the generation of voltage across the detector as a function of time is shown. So here we can see that in the upper panel, when the charge is collecting in the detector. During that time, the voltage across the detector is rising. Once the complete charge collection happens, charge collection stops in the detector, we achieve the maximum voltage across the detector, and then that voltage basically starts decreasing with time. Radiation detectors modes of working. The rise time. Rise time means the time taken for the preamplifier output voltage to reach its maximum value is called the rise time. The rise time of the detector is determined by the charge collection time of the detector and is not affected by the value of the components of the circuit. The decay time of pulses is determined by R and C. Usually we take RC around 1 microsecond. This RC is nothing but the called the time constant. So the decay of pulses is determined by RC. Usually we take time constant RC is equal to 1 microsecond. Leading edge is detector dependent while trailing edge is circuit dependent. This is very important. So we can basically adjust the time constant, because the time constant for the leading edge, there is RC combination in the input stage, there is RC component in the output stage. So by choosing an appropriate time constant, we can basically play with the rise time and decay time of the detector. Timing resolution of such detector is as fast as the charge collection time. Detector work in this mode when used to detect ionizing radiations. Successive interactions must be separated by some finite amount of time, which we call as detector dead time, to produce two separate signals. So this is basically, you can see it as a disadvantage with pulse mode, because in the pulse mode each interaction is counted individually. So each interaction is happening and each interaction is producing one pulse, and all the pulses are processed individually. So we can say that if we want to get information about the interactions, each and individual interactions, then the two pulses resulting from two separate interactions must be separated by some fixed time. Only then we can count them individually at the output. So this time between the two successive pulses is called the detector dead time. So one of the important thing, because when the radiations enter in the detector, they interact with the detector continuously, but we can count only when the two interactions are happening at certain interval of time. So it means in this case basically the disadvantage is most of the interactions are not getting counted because of the detector dead time, and this dead time becomes a very important issue in the measurements. So when we are having the fast data rate or fast counting rate, for fast counting rate we choose a detector whose dead time is very low. Otherwise we will lose major portion of information. So successive interactions must be separated by some finite amount of time, which is called detector dead time, to produce two separate signals. Interactions happening during dead time are lost, definitely, because the interactions are happening at a very fast rate, but our detector and the associated electronic components have some limit that they can process individual pulses. They take some time. So during that time, no other pulse is basically processed. So during the dead time, whatever interactions are happening, they are not getting counted. So interactions happening during dead time are lost. Also, if second interaction occurs close enough to the first one, it may distort signal from the first interaction. This is also very important. So dead time is determined by the component in series with the longest dead time. GM counters have the longest dead time. So if the GM counters basically, we know that the interactions basically take place in the gaseous medium. So GM counters have the longest dead time. They have dead time ranging from tens to hundreds of microseconds, while most other detectors have dead time less than few microseconds. Radiation detectors, pulse height analysis. So we have seen that pulse mode is better than the current mode of working. So here in this slide we are going to look more deeper into the pulse mode of working of detectors. In pulse mode, the amplitude of each pulse is proportional to the energy deposited in the detector by the interaction causing that pulse. What does that mean? That whatever pulses we record across the detectors, that is the output of the preamplifier, the height of those pulses, which is basically nothing but the amplitude of those pulses, basically is proportional to the amount of charge collected in the detector corresponding to the interaction of that radiation. So in this case we can say that as the different energy photons on interaction with the material of the detector produce different number of charged particles. So charge collected due to each interaction will be different, and therefore different amplitude voltage pulses are observed across the detector, that is at the output of the preamplifier. So in some way we can say that the amplitude of detected pulses basically gives an idea about the energy deposited in the detector by the radiation. Output pulse from preamplifier is too small, that is around few millivolt, to put into an analog to digital converter, so need to be amplified and shaped properly. Now since we record the voltages at the output of the preamplifier, the gain of the preamplifier is not very high, so output pulses are basically of a small size, or you can say that of a small amplitude, and they are not very well shaped. To get the meaningful information from these pulses, we need to amplify them and shape them properly. So in combination with the preamplifier, we need to put an amplifier, normal amplifier. The preamplifier voltage signals are basically fed to the amplifier, which shapes these pulses and increase their amplitude, so that the output of the amplifier can be put into the analog to digital converter, which converts these analog voltage pulses into digital signal, and then these digital signal can be counted with the help of some counter. Radiation detectors, pulse height analysis. By converting voltage into digital number, it can be arranged into certain discrete channels or bins to form a spectrum. So here in this slide, basically the block diagram is given where the detector, where it is shown that the detector output is fed into the preamplifier, preamplifier output is fed into an amplifier, and the amplifier output is fed into the multi-channel analyzer, which is basically has one ADC, that is amplitude to digital converter, and then basically we can see the output either in the form of a spectrum, because we can convert these digitized numbers in the form of certain discrete channels or bins. So we can see the spectrum on the screen of MCA, or we can basically couple a counter after ADC, so that the number of interactions can be obtained rather than observing the spectrum. MCA then shows the energy spectrum. Peaks indicate the hitting of same energy radiation in a number of time, same energy radiation a number of times, which we call as events in the detector. Radiation detectors, pulse height analysis. So we continue our discussion about the pulse height analysis. Now energy resolution can be defined for detectors in the pulse height analysis. Now we want to understand what is the energy resolution and why it is so. If we observe the spectrum in the MCA, then we find that each gamma ray peaks are not in the form of line, but they have some definite width. The width of these gamma rays is a measure of resolution of the detector. First important question comes in mind, that why the gamma energy peaks in the spectrum have width. Now energy peaks in the spectrum have width due to number 1, drift in the characteristics of the detector, because the detectors have some properties, basic properties which may change. Second, statistical noise due to finite number of charge collected. Statistical noise means the same energy radiation can have little different number of, can produce little different number of charge carriers in that detector. So that difference, small difference in the number of charge carriers produced by identical energy radiations is called a statistical noise. So statistical noise is due to finite number of charge collected. Number 3, random noise in the detector, because in the detector we have various elements. So it may happen that some of the elements can pick up noise, or if not detector, then we know that in the detector we connect an amplifier, a charge sensitive amplifier, which is prone to some kind of noise pickup. So because of all these reasons, we can say that there can be random noise in the detector. The statistical noise is minimum fluctuation in the signal which will always be present. So we can see that the energy width, the width in the energy peaks in the spectrum is due to 3 different processes: drift in characteristic of detector, statistical noise due to finite number of charge carriers, and third are the random noise in the detector. Now out of these 3 things, we can control up to some extent, we can control the random noise and drift in the characteristics. So it means for an ideal detector, there will not be any drift in the characteristic of detector, and there will not be any random noise in the detector. So if we control them 100%, even then a statistical noise will be there. So it means we can never have the gamma energy like lines in the spectrum. They will definitely, or even for the ideal detector also, there will be some width of the gamma energy peaks, and that width is because of the statistical noise. So statistical noise is the minimum fluctuation in the signal which will always be present. It is shown, the behavior of the gamma ray peak in the spectrum is shown on the picture in the right hand side. Here various terms are being marked like FWHM, delta E, E0, H half, H, etc. for a photo peak. Radiation detectors, pulse height analysis. So we continue our discussion about the pulse height analysis. So here in the previous slide we have seen the picture of the gamma ray energy in the spectrum, where FWHM basically is shown. FWHM is nothing but the width of the gamma ray peak when the detector counts are 50% of the maximum number of count in the peak. This FWHM is basically the measure of resolution of the detector. So statistical noise arises as charge Q deposited in the detector is not a continuous variable but a discrete which varies from event to event. Resolution of detector depends on the type and energy of the radiation. So here basically what we were discussing as FWHM, that full width at half maximum. This is the expanded form of FWHM. It is nothing but the width of the gamma energy peak corresponding to 50% of the count of the maximum number of count in the peak. So resolution R is given as equal to FWHM upon E0, where E0 is the centroid, or you can say that E0 is the energy of the gamma radiation. For detector type, in the bottom of this slide, a table is given in which typical resolution of different type of detectors are being given for different kind of radiations. So, in the first column, detector type is given, on the second column radiation is given, and in the third column resolution in terms of FWHM upon E0 is given. Now, as we can see that for germanium detectors, for gamma rays, we have resolution around 0.2%, whereas for sodium iodide, for gamma rays the resolution is around 10%, and for diodes alpha particle resolution is around 1%. So, you can see that for the gamma rays, for different kind of detectors we have different resolution. Radiation detector pulse height analysis. We will look into the issue of pulse height analysis with radiation detectors. More charge carriers created in the detector, better the resolution. It means resolution depends upon the number of charge carriers created per interaction in the detector. If an incoming radiation can create large number of charge carriers, then in that case the detector will have very good resolution. So, resolution is a function of number of charge carrier created per interaction. In the pulse height analysis, we can also define a term which is called Fano factor. What is Fano factor? A correction factor introduced adjust observed to Poisson theory predicted variance. Fano factor is defined as the ratio of observed variance upon Poisson predicted variance, and R is equal to R means the resolution depends upon the Fano factor, that is R is equal to 2.35 square root f by n, and this is nothing but the resolution limit since variance is sigma square. For semiconductor detectors, Fano factor is very much less than 1. For scintillation detectors, Fano factor is around 1. So, FWHM for a gamma ray peak is basically a combination of various process. So, FWHM square total is equal to FWHM square statistical plus FWHM square noise plus FWHM square drift plus and so on. Radiation detectors pulse height analysis. So, we see that gamma energy spectrum, we see that the gamma peaks follow the Gaussian distribution. The gamma peaks are of Gaussian shape. If random fluctuation is only source of uncertainty in resolution, then peaks in the energy spectra have Gaussian shapes. So, this basically, this statement shows the conditions under which the gamma energy peaks in the spectrum will show the Gaussian kind of distribution. What is that condition? That if the random fluctuation is the only source of uncertainty in resolution, then only the peaks of energy spectra will have Gaussian distribution. And Gaussian distribution by definition is Ge is equal to A by sigma root 2 pi exponential minus E naught whole square upon 2 sigma square, where E is the energy of the photon, E0 is basically the maximum energy of or the centroid of the gamma energy peak, sigma square is the variance, A is the area of the peak. So, here basically sigma is a function of FWHM, it can be given as FWHM upon 2.35. So, resolution limit is given by R is equal to FWHM upon E0, that is equal to 2.35 upon square root of n, where k is equal to constant for a given detector. Peak to total. Peak to total is the next important thing that we define in case of pulse height analysis. Peak to total basically is a measure of the goodness of a detector. That is, in an ideal spectrum, what we want is more photo peaks than background. So peak to total is an indication of how much photo peaks are there out of the total statistics observed. Why that thing is important? Because photo peaks indicate the complete absorption of photon, whereas the background indicates inefficient absorption of gamma photons. So not all interaction result in full energy peaks. So peak to total is defined. So peak to total is equal to total counts under all peaks divided by total counts in the spectrum, or R is equal to epsilon peak upon epsilon total. Radiation detectors pulse height analysis. Now in the pulse height analysis, there is one more important thing which is defined, that is called detection efficiency. Detection efficiency is the quantity which tells us that how efficiently a given detector is counting radiations. The ability of radiation detector to count interactions is called detection efficiency. Detection efficiency can be defined in terms of absolute efficiency. Absolute efficiency means the number of pulses recorded upon number of quanta emitted by the source. So basically the absolute efficiency means absolute efficiency is the function of the positioning of detectors in the geometry, because absolute efficiency is nothing but how many counts we are getting per second divided by how many counts are emitted from the source of radiation. So it means there is a big play of solid angle in measuring the absolute efficiency, and solid angle depends upon the positioning of the detector, that how close or how far the detector is put from the source of radiation. So if we put detector close to the source of radiation, the absolute efficiency will be high. If we put the detector far from the source, the absolute efficiency will be low. Next important efficiency is the intrinsic efficiency. Intrinsic, as the name suggests, it is the property of the detector. It has nothing to do with the geometry, that where the detector is put. It basically counts that how many radiations have entered in the detector and how many of them have been counted. So intrinsic efficiency is defined as the ratio of number of pulses recorded upon number of quanta incident on the detector. So it is intrinsic efficiency is nothing but it is the characteristic property of the detector. So we can define, for a given detector we can define the intrinsic efficiency, whereas the absolute efficiency is a function of geometry, that where the detector is put in the setup. For isotropic source, absolute and intrinsic efficiencies are related as epsilon intrinsic is equal to epsilon absolute into 4 pi upon omega, where omega is the solid angle given by A by d square. So students, let us summarize what we have learnt in this module. We have discussed very many concepts, but now it's time for us to recap what we have understood so far, or what we have learned. The first thing we learned in this module is that radiation detectors work in the current mode and not in the pulse mode. So, radiation detectors work in current mode and in the pulse mode. Second important thing that we learned is that pulse mode of working is better than the current mode, as in this mode type and the energy identification of incoming radiation is possible. Third important thing that we have learned is that detectors in pulse mode are slow, so preferred only if data rate is low. Detectors working in the pulse mode has gamma energy peaks in the spectrum. Every detector has properties like resolution. Resolution is the width of energy peaks, efficiency, which is nothing but the ability of detection, and peak to total, which is nothing but the useful detection. Thank you.